Okay, here we talk about the energy stored in an electric field, or the energy stored in the capacitor. So here you have the U as the potential energy, and yeah, actually you can imagine, suppose there is a capacitor without any charges, then there will be no energy stored there. And just like this, suppose there's a capacitor without any charge, then of course there will be no energy stored there. And after it stores some charges, like there is some positive charge and then negative charge on both the top and the bottom plate. This is Q, this is negative Q. This is Q, this is negative Q. Then there must be some energy there to put some charges in the capacitor, because in this case the positive charge and negative charge will attract each other, so there it will store some energy inside, and of course there will be some electric field, and actually we need some energy to generate this kind of electric field. So in this case the U is the potential energy stored there, and then it is done by, we have V is the potential difference between the parallel plate, and yeah, so it is calculated by accumulating charges from 0 to small q, and then we do this is to at the very beginning there will be no charges, and then we try to put small amount of a dq prime, negative dq prime, and then start to accumulate from 0 to small q, and then we take the integration to find the total and potential energy stored in the capacitor. So in that case, we have V is a function of a Q prime, because we always have a Q equals CV, or Q prime equals CV. Because we have a small q here, so we have a prime, so that we can distinguish this Q prime and Q. And yeah, actually V is the function of Q prime, which means that Q prime equals CV, so we have a V equals Q prime over C, Q prime over C. So we'll put this thing here so that we can do this integration, which is easy because it is a polynomial. You take the integration is Q squared over 2. So we have Q squared over 2C, or you can still use Q equals CV, so that we can have 1/2 CV squared, 1/2 CV squared, which is usually used 1/2 CV squared. Okay, so here it also mentioned a variable called energy density. Okay, energy density means the energy stored in this region. So it is the energy per unit volume. The energy per unit volume is called the energy density. So the potential energy per unit volume in the field of the magnitude is E of magnitude E is this one, small u. We use small u to stand for the energy density. We use a big U to stand for the energy itself. So these two look similar. 1/2 epsilon naught E squared. Something similar. Okay, so you can imagine if it is a parallel plate capacitor, parallel plate capacitor. So you can imagine U, small u is capital U divided by their volume here. The volume is like the cross section. The cross section here is A, and the distance between the parallel plate capacitor is small d. So the volume between the capacitor is A times D. This is the cross section area times the height. So this is the volume. This is a follow. Okay, so next we have U to be 1/2 CV squared. So we have 1/2 CV squared over AD. And if you still remember, the capacitance for the parallel plate capacitor is like epsilon naught A over D, epsilon naught A over D, and then we have V square, V square. And if you still remember, V is E times D, V is E times D, V is E times D. In chapter 24, so we have a E times D quantity square all over AD, all over AD. So we can do some simplification, do some cancellation. A and A can be cancelled, and then this is D, and D in the denominator, in the denominator, and this D square is in the numerator. So this D, and this D square can be cancelled. So finally, we have 1/2 epsilon naught E squared. So it's just a demonstration how to verify this to be correct using the parallel plate capacitor. For other types of capacitor, it's still correct. Actually, I seldom use this one, but in physics textbook, it really use this one to physicians like this kind of value. And actually, in chapter 33, I think in chapter 33, when we talk about the EM wave, or the electromagnetic wave, then we will come up with this expression again, because at that time we'll consider something called the Poynting vector for the electric field, which is the energy carried by the EM wave. Then it is related to the energy stored in the E field and also the energy stored in the magnetic field, something like that. So because you can see we have a electromagnetic wave, means it has some component of an electric field and also the magnetic field. So some energy stored in the electric field, some energy stored in the magnetic field. So this is half of the energy density carried by the EM wave, and we'll come up with this later. Okay, so here is a sample problem. So it says, in an isolated conducting sphere whose radius R is 6.85 centimeter, has a charge Q, how much potential energy is stored in the electric field of this charged capacitor? So for part A, so for capacitance of a spherical capacitor, and it only mentioned the radius R, which means it has no outer sphere. So the capacitance is 4 pi epsilon naught capital R, like this. Okay, so we can just plug in the number to or maybe we can find the energy stored there by Q square over 2C. Q square over 2C. Usually we use 1/2 CV square, but Q square over 2C is actually the same thing. Because here we know the charge, Q, so we can make use of Q square over 2C, and then this C is 4 pi epsilon naught R, so we have a Q square over 8 pi epsilon naught R. Okay, like this. So we can plug in the numbers. So 1 over 4 pi epsilon naught is k. So we have 8.99 times 10 to the 9th power over 2. Over 2 is 8 pi epsilon naught. Okay. So times 1.25 nano is 10 to the minus 9th power quantity square over r is 6.85 centimeter. So 0.0685. So this number is 1.03 times 10 to the minus 7th joule. Okay, for part B, what is the energy density at the surface of the sphere? Okay, so actually for the spherical capacitor, if you do not lecture, I don't think you maybe you can remember. Actually, if you apply the Gauss law here, you will know that the E field is inversely proportional to the square of the radius. So here we'll have E equals K times Q over R square, like this. So if you can't really get right, you can go back to that figures, and then you try to apply the Gauss law, then you can get it. Okay, so here we have U equals 1/2 epsilon naught E square. So this number is well, or maybe we can just write it as 1 over 4 pi epsilon naught Q over R square, and then we can plug this one here, so that we have 1/2 epsilon naught, and then E square will be 16 epsilon naught square, pi square, and then times Q square over R to the 4th power. So it turns out to be 2 times 16 is 32, and then pi square, and then epsilon naught, and then R to the 4th power, and then on top we have Q square. So we can plug in all the numbers. Q is 1.25 times 10 to the minus 9th power quantity square, all over 32 pi square, and then times 8.85 times 10 to minus 12, and then times capital R is 0.0685 to the 4th power. So this number is 25.4 times 10 to the minus 6 joule per meter cube. So the SI unit will be joule. Joule is the SI unit for the energy, and then the volume is meter cube. So we have a J over meter cube for the SI unit of energy density, or you can simply write it as a 25.4 mu J per meter cube. Both are correct. Any questions? Okay, so next we talk about some hardcore physics. I think it is quite hardcore, but you don't necessarily need to understand very deeply. But yeah, maybe we can do some calculation about that. But yeah, it will be fine if you really get all the idea inside, because it is quite hardcore. Okay, so here we talk about the capacitor with a dielectric. So here is a simple experiment to explain the idea. So it says if the space between the plates of a capacitor is completely filled by a dielectric. Dielectric in Chinese is called 电介质 dielectric. Okay, dielectric material. The capacitance C in vacuum. Originally, we consider if we don't really fill in the dielectric, we assume it is vacuum or with air. With air or with or if it is vacuum. For electricity point of view, the difference is not quite large, so we will usually consider it is a vacuum or effectively in air. Yeah, so originally for a capacitor we just assume it is vacuum or with air. Then now if we suppose we try to plug in some dielectric material inside the parallel plate or inside any size of any structure of a capacitor, then it's multiplied by the material dielectric constant kappa. Here with a kappa, which is a number greater than 1. So it is like originally in many of the equation we will use epsilon naught or 4 pi epsilon naught, something like that, if we consider there is no dielectric. But here if we plug in the dielectric with the dielectric constant called kappa, then we will just substitute epsilon naught to be kappa epsilon naught, or 4 pi epsilon naught to be 4 pi kappa epsilon naught, something like that. So it says, this is a highlight, it says in a region completely filled by a dielectric material or dielectric constant kappa, all the electrostatic equation containing the permittivity constant epsilon naught are to be modified by replace epsilon naught with a kappa epsilon naught. So yeah, so there's a simple rule if we have dielectric. Okay, so next let's see this phenomenon. What does it mention? So for the left one here. So if the potential difference between the plate of a capacitor is maintained, so as by the presence of the battery B, the effect of the dielectric is to increase the charge of the plates. Increase the charge of the plate. So here we doesn't change the potential difference of the battery. So here we have a V. We have V. Like this. We have V from this node to this node. So this is V and 0. Maybe we can call it the ground here. Call it the ground. So we have a 0 volt V. This is 0. This is V. Like this. So in this case, if we just plug in this dielectric, then we can see that the charge on the plate increases. The charge on the plate increases. There are less charge here and more charge here. And for the capacitor, you can imagine Q equals CV. Q equals CV. Now we try to fix the V. We don't change it. Now if we just plug in the dielectric, then we can see the charge amount increase, which means that Q increase, also C increase. Q increase, C increase. Okay, this is the first case. And for the second case, now if the charge of the capacitor plate is maintained, okay, so we shouldn't have this too, or maybe I should still have this too. Yeah, if the charge on the capacitor plate is maintained, as in this case, by isolating the capacitor, the effect of the dielectric is to reduce the potential difference between the plate. Okay, so this means that still we have a Q equals CV. This time, we don't really change the charge. Which means that we suppose we don't have any I equals 0. We don't have any current going in or going out from the capacitor. We maintain the charges on the capacitor to be a constant. Then in this case, we keep this one constant. We keep the Q constant. So before we plug in the dielectric, the voltage or the potential difference is higher. After plugging in the dielectric, the potential difference becomes smaller. So it's feel like V decrease, C increase to maintain this Q to be constant. So for both of these cases, we can also consider that the capacitance increase. So for both cases, capacitance increase. Okay. So here comes the hardcore part. It tried to explain what is really the dielectric. So yeah, so here it says an electric field is applied producing partial alignment of the dipole. Thermal aggregation prevents completely alignment. So this is something like the molecule of the something like the air. You can imagine it is something like or maybe not necessarily air, or maybe it can be the water, H2O, something like that. If you still remember the H2O, H plus. Then it is a dipole. Okay. So for the H2O, yeah, if you apply the electric field to the dipole, then it may try to align, but not perfectly align. It will try to swinging back and forth over the electric field direction, something like that. So electric field is applied producing only partial alignment of the dipoles. Thermal aggregation prevent completely alignment, because if it is completely alignment, then it doesn't really move at all. But for the initial state, there may be some potential energy, so it may swinging back and forth to convert the potential energy to kinetic energy back and forth. Okay, now we consider the polar dielectric. So it says the molecules with a permanent electric dipole moment showing their random orientation in the absence of an external E field. So now, this case is absence of external E field. Then the orientation of the dipole will be randomly, and it makes all the dipole will cancel each other. So it feels like this one will not no E field. It will not generate any E field without the external E field. So you need to distinguish. There will be some E field generating outside and yeah, for the coming statement. But here we assume that there is no external E field, no external E field. Then the dielectric will generate no E field. Although all of them are dipole, but the orientation of them are somehow like randomly. So some of the dipole point to this way, some of the dipole points to the another way, then they generate some E field, but it turns out to be all the dipoles cancel each other. Okay, so now the first case is that if there is no external E field, then it will generate no E field. So inside the dielectric, there will be no E field. Now we try to apply the E field externally. The applied E field align the atomic dipole moment. So if we apply the external E field, then the dipole inside the dielectric will be aligned. So suppose the E field point to the right side, the positive charge, there will be a force dragging it to the right side for the positive charge. And for the negative charge, the force will be opposite to the E field direction. So the negative charge will point to the right side. So it's looking like this. And in this case, yeah, you can try to regard this one. So this is two parallel plates from the outside. So you can regard this one. This one is a big capacitor to generate the E field pointing to the right side. And this part is the dielectric. This part is the dielectric. So for the dielectric, the dipole moment will somehow point to the right side. And in this case, this dipole moment all align to the right side, then it will generate some E field point to the left side. It will generate some E field point to the left side. This is the E field generated by the dipole. Generate by the dielectric. Generated by the dielectric. This one. So the field of the aligned atoms is opposite to the applied field. So this E prime points to the left side, cancel part of the E0. The E0 this is the external. This E0 is external E field. External E field generated by this big capacitor. So in this case, part of this E prime, part of the E0 will be cancelled by this E prime. So E is the total E field inside the dielectric, which is smaller than the external E field. So this is the case. I usually will say a analogy to the dielectric. It's somehow like if we just dismiss the class or during the break, then you may talk with other students. So you may not facing to the board here, to the screen. It is somehow like you are randomly oriented, although you are still limited by the desk. So you usually will facing this side, but not necessary. But during the class, you usually will facing the screen. You you should be listening, or at least you are pretending you are listening. Yeah, so this is somehow like the dielectric. Okay, so here we come to the mathematical part. So here, yeah, so here it says inserting a dielectric into the capacitor, causing induced charge to appear on the face of the dielectric, weaken the electric field between the plates. It always generates some E field opposite to the external E field, but the E field generated by the dielectric will not be larger than the external one. It can only weaken it, but not reversing it. So the induced charge is less than the free charge on the plate. Okay, so yeah. So when the dielectric is present, Gauss law may be generalized to this case. So as mentioned before, if we have dielectric, we will change epsilon naught to kappa epsilon naught. So maybe you will say, let me just put this kappa outside, but in this textbook it tells you that maybe the dielectric is not so uniform, so maybe he just put this kappa inside the integration like that. So here is yeah, so it's nothing but yeah, it's almost the same as the normal Gauss law, like this, Q enclosed. So the only difference is that we put this kappa there. So Q is the free charge. Yeah, any induced surface charge is accounted for by including the dielectric constant. So when we try to use this formula, we don't try to consider the induced charge of the dielectric field, because this kappa already account for it. If you also consider this Q prime, or you just cancel part of the Q, then you double account this effect, then you will make mistakes. So just remember that when you use this equation, then you just forget this negative Q prime. But also, although sometimes you are supposed to find this Q prime, but you use another method. In one of the selected problem, you have an example to consider how to calculate the Q prime. Okay, so yeah, so here, yeah, actually in electromagnetism, there will be a variable called D, which is epsilon naught kappa E. So yeah, so but in this textbook we seldom use this variable, so you can just forget it. Unless you are ECE student, you might need to take the electromagnetism course in the next semester. Yeah, but it's just a variable, nothing special. Okay. Okay. So let's see a sample problem to see how we can make use of this Gauss law with the kappa there. So here it says a parabolic capacitor whose capacitance C is charged by battery to the potential V between its plates. The charging battery is now disconnected, and a porcelain slab is slipped between the plates. Okay, so what is the potential energy of the capacitor before the slab is inserted? Okay, so before this is of course simple. Yeah, so for the potential energy is nothing but Ui equals 1/2 CV square. 1/2 CV square. So C is given, V is given, so we can just plug in the number. C is 13.5 times 10 to minus 12, and then times V is 12.5 squared. So this is 1.055 times 10 to minus 9 joule. Okay, so for part A, it is easy, just a warm up. And yeah, so for part B, what is the potential energy of the capacitor slab device after the slab is inserted? Okay, so here we would like to find UF equals not actually 1/2 CV squared, because here the voltage will change. The case here is like here at the very beginning, we have a capacitor without dielectric, and then this V between the parallel plate is 12.5, and then of course in this case this is the capacitance. C equals 13.5 picofarad, and then there are some charges, Q, negative Q, like this. Now we try to disconnect the battery so that there will be no current or no charges can going in or going out from the capacitor. So we disconnect the battery. Disconnect battery. And then the third step is to insert the dielectric. So in this case, C will increase, but Q doesn't change. Q is fixed. So we have a Q equals CV. So Q is fixed, C increase, so V will decrease. So we cannot directly use 1/2 CV square. We would like to see C prime. Now it becomes C prime. C prime will be 6.5 C, because kappa is 6.5. It's a parallel plate capacitor. If you still remember, C is epsilon naught A over D for parallel plate capacitor. Now after inserting the dielectric, it should become C equals kappa epsilon naught A over D. C prime becomes kappa epsilon naught A over D. So it should be kappa C. So we have a 6.5 C here, and UF will be Q squared over 2C prime. We make use of this one. So Q is 13.5 times 10 to minus 12. This is C. This is original ring. So this is the original charge accumulate there, but it doesn't change. So we can have this Q, and then over 2 times 6.5 times 13.5 times 10 to minus 12. So UF becomes 1.62 times 10 to minus 10 joule. Okay. So this is 1.62 times 10 to minus 10. And before UI is 1.055 times 10 to the 9th power. This is 1.62 times 10 to minus 10. So some energy disappeared. Actually, part C, what is the capacitance C0 before the Okay, so maybe I can just explain it here. So actually, W equals UI minus UF will be 1.055 times 10 to minus 9 minus 1.62 times 10 to minus 10. So this number is 8.93 times 10 to minus 10 joule. Actually, some work done involved here, and the energy is stored in the dielectric itself because as mentioned, if you apply some electric field to the dielectric, the dipole inside the dielectric will be aligned. So in this case, it will generate some E field opposite to the external E field direction. And in that case, the dielectric should store some energy, which is actually this number, although it's not asked in this question, but yeah, just let you know that. And actually, if you really put this dielectric inside the capacitor, it is like the capacitor itself will absorb this dielectric inside the capacitor because it tries to store some energy inside. So here we have another sample problem. It says a parallel plate capacitor of a plate area A and separation D. So a potential difference V0 is applied between the plate. The battery is then disconnected, so similar to the previous case. And a dielectric step of thickness B. So the total distance, total separation is small d, but the thickness of the slab is only small b. The dielectric constant copper is placed between the plate. So assume A, D, V0, B, and copper. So what is the capacitance C0 before the dielectric slab is inserted? So still part A is a warm up problem. So C0 is epsilon naught A over D. So epsilon naught is 8.85 times 10 to minus 12. And then A is 105 centimeters square. So you need to divide it by 10 to the fourth power to make it a meter square. So it is 0.0115 to make it meter square. And then over D is 0.0124. Okay. So C0 is 8.21 times 10 to minus 12 farad. Did I forgot to mention the SI unit for the capacitor? Okay, so for the SI unit for the capacitor, the SI unit is farad. Farad. So capital F. Farad. Okay, so yeah. Or you can write it as 8.21 picofarad. Okay, so this is part 8. And for part B, what is the free charge appears on the plate? So Q0 is C0 V0, so nothing special. 8.21 times 10 to minus 12 is C, and then V0 is 85.5. So Q is 7.02 times 10 to minus 10 C Coulomb. So you need to try to memory a bit because the SI unit for the Q is C, the SI unit for the C is F. something like that. Yeah. Okay, so for part C, what is the electric field E0 in the gap between the plate and the dielectric slab? Okay, so here we try to use the Gauss Law. And yeah, E0 first. Because when we consider E0, it is outside the slab, which means the external E field generated by the capacitor. Inside the slab, we use another notation. So yeah, between the plate and the slab, which means this region. So we can use the Gauss law for the Gaussian surface 1. So we write out the Gauss law. So epsilon naught integration of E dot dA equals Q 0. So maybe Q here. This is Q. Okay, so here epsilon naught and then E0 times A equals Q. So here we have a E0 equals Q over epsilon naught A. So Q is maybe Q0 there. Just maybe Q0, yeah. Q0, yeah. So 702 times 10 to minus 12 all over 8.85 times 10 to minus 12, and then times 0.0115. So this number is 6,900 volts per meter. Okay, so this is the external E field. Okay, so for part D, what is the electric field E1 in the dielectric slab? So E1 should be pointing downward also. This is E0. Although E1 is smaller than E0. E1 is smaller than E0. Because a part of the E field generated by the dielectric is in the opposite direction. This E prime is generated by the dielectric. It will cancel part of the E0. So in this case, we apply the Gauss law for the Gaussian surface 2. So here we have epsilon naught integration of a kappa E 1 dot dA equals negative Q0, like this. Okay, so here E1 is pointing into the Gaussian surface. So this one is a negative number. And yeah, so this is also a negative number. So it turns out to be epsilon naught times kappa negative E1 times A equals negative Q0. So we have a negative sign on both sides, so they cancel each other. And it turns out to be E1 equals Q0 over kappa epsilon naught A. Okay, so it is like 7.02 times 10 to minus 12, and then over kappa is 2.61, and then times 8.85 times 10 to minus 12, and then times 0.0115. Okay, so this number is 2,640 volts per meter. So the E field is much smaller than E0. E1 is much smaller than E0. E0 is 6900, 2 times 61 times larger than this one. Okay, so this is part D. And for part E, it asks you what is the potential difference V between the plates after the slab has been introduced. So we have a E0 here, E1 here, and E0 like this. Okay, so to know the potential difference, V between this plate and the bottom plate. So we do the line integration. But here for parallel plate capacitor, the E field is uniform over this region, and over this region. So the total V is like EDS from negative to positive. And it is nothing but E1 times B, because it is uniform. So the integration is like the E times the length. So the vertical length of the slab is small b. So we have E1 times small b to be the potential difference within the slab. And then outside this slab, this region and this region, we don't actually know the distance between the top plate and the slab and the bottom plate, but altogether it should be D minus B for including this part and this part. So we add E0 times D minus B. We don't really need to care about what is the height of this part and the height of this part. Okay, so this is 2640 times B is 0.0078 plus 6900 times this one is D is 1.24. So 0.0124 minus 0.0078 like this. So it is 52.3 volts. 52.3 volts. Originally V0 is 85.5. So here it turns out to be 52.3 volts. Okay, so we still have part F, which is the final sub-question. So it asks, what is the capacitance with a step in place between the plate of the capacitor? So here we have a C, the final capacitance, to be Q0 over V, because Q0 doesn't change from start to the end. And we already find V is 52.3, so it is nothing but 702 times 10 to minus 12 over 52.3 volts. So this is 13.4 picofarad. 13.4 picofarad. Yeah, if you still remember, C0 is this one, 8.21 picofarad. So in this case, C also increased, but not necessarily 2.61 times, because the thickness of this slab is not the same as the plate separation. So it only increased by 1 point something times. It depends on the thickness of this slab. Okay, so that's all for this chapter, and let's have a 10 minutes break.